Video, I'm going to look at how we can calculate the uncertainty in something that we've taken the logarithm of. So I'm going to do this in the context of simple harmonic motion with a mass spring system. So first, let's revise some of the stuff that we should know already. So we should know the resolution of a measuring instrument is the smallest division on a measuring device. Say on a meter ruler, that's 1 millimeter typically. So we're going to need this because for some of our values, we may need to estimate the uncertainty in a measured value using this. So if we have a digital measuring device, its uncertainty is equal to its resolution. So for a stopwatch, which is typically has a resolution of 0.01 seconds, the uncertainty is also 0.01 seconds. If we use an analog measuring device, the uncertainty is equal to the resolution divided by 2. So one reading from a meter ruler, for example, has an uncertainty of 0.5 millimeters, but I'm going to come back to that a little bit later on because it's a little bit more complicated than that. We should also know that if we have repeat readings of the same measurement, so we've kept everything the same and just repeated a measurement, that the range of those repeats divided by 2 gives us the uncertainty. And that's really all the things we need to work out uncertainty in logarithms. So to give you the context that I'm going to do this in, so say we want to investigate the time period of a mass spring system. And when we just thought about it, so we were the scientists who discovered all this stuff, we thought maybe its initial displacement might affect time period, we thought mass might, we thought spring constant might affect it. So we know a bit more than that now, but that's how they would have had to think. So I'm going to represent this equation in the form you can see on screen. So T is equal to a constant A multiplied by amplitude to the power of x, mass to the power of y, and spring constant to the power of z. So we don't know anything about the relationships, which is why I've kept it very general like that, with powers and a constant. So what we're going to try and do is design an experiment to find out a, x, y, and z. So first off, we're going to try and find x. So we know that the equation should be time period is 2 pi times root m over k. That's what you learn about for mass spring systems. So when we do an experiment, we should find out our value of a is 2 pi. We should find out x is 0 because amplitude isn't in the equation. We should find out y is 0.5 because it's square root. Time period is proportional to square root m, and we should find z is minus 0.5 because time period is directly proportional to 1 over root k. So that's what we should find. So let's have a look at how we would actually find those powers. So the first thing we're going to do is we want to look at finding x. So we're going to keep mass and spring constant exactly the same throughout. So we can change this equation to essentially time period is equal to a new constant b times a to the power of x. So b is just taking all those other things we're keeping the same to make it simpler. And we're going to turn that into y equals mx plus c form. So we're going to do that using logarithms, which is why I'm using this as the context. So if we want to find out a power, that's where logarithms are useful to us. So first we take the log of both sides. I've used base 10 for this whole experiment, but you can use whatever base you like. So the first thing we can do is split up b and a to the x into log b plus log a to the x, and then we can bring the x out in front of the log, as you should know from learning log rules in maths. So we can see from here, if we plot a graph of log t versus log a, as long as we use the same base for both, the gradient of that graph is going to give us x, and the y-intercept is going to give us log b, but we're not really interested in the y-intercept at this point. So that's what I'm doing. I'm going to collect some. Here it is. So we've got amplitudes down the left, which were changed between 1 centimeter and 7 centimeters. But my meter ruler measures to the nearest millimeter, so that's why we've got 3 decimal places. I did this by, I measured the time for 10 time periods and divided by 10 to get all my times there. We've again got the average time period. I've calculated what the uncertainty in those time periods is by using range over 2. And then I've got log of time period and log of amplitude there over on the right-hand side. So the first thing I did is I calculated the average of my uncertainties for the time period, because I'm going to use that later on. That gives me a value of 0.017 seconds as the average uncertainty in my time period measurements, which is pretty good in the context of timing things. So then I'm going to plot a graph of this data. So I've got log t against log a. So when I first look at this graph, this looks bad because we were expecting to see a gradient of 0. So just looking at first inspection, that doesn't look very good. However, when I use the equation feature, then we can see from the equation the gradient is 0.0322, which is quite close to 0, so it's looking promising. But realistically, this isn't enough information to judge whether the experiment justifies the actual equation or not. We need to look at the uncertainty in the gradient to do that. So the first thing is, as you can see from the graph previously, I've picked 2 points on the graph which I use to figure out the gradient, and you can see the values from the graph, and I've pulled them onto this slide here. So we can see we've got a value for the change in log time period and the change in log of amplitude. We've got values for that. So what we need to do is find out what the uncertainty in the change in log t and the change in log a are, so then we can calculate percentage uncertainty in the change in those logs to give us the percentage uncertainty in the gradient. That's how we're going to go about this. So the first thing I did is I've taken the first value of log t, which was minus 0.161. I've done 10 to the power to figure out what the actual time was for that value. We already worked out the uncertainty in time period is 0.017 seconds. So this value of 0.69 seconds is plus or minus 0.117. So that gives us the maximum and the minimum possible values of the time period. I've then found the logs of those maximum and minimum values. I found the range of those and divided them by 2. That gives me the uncertainty in the log of that time period. I repeated exactly the same process with the minus 0.185 value. So I figured out what the actual value was, added and subtracted the uncertainty, took logs of those, and found the uncertainty in that one as well. And then what is to find the uncertainty in the change in log t. It's those two uncertainties added together, so 0.022. We divide that by the value of the change of log t, 0.024, and we can see we end up with 92%, which seems very high, but remember we're dealing with very, very small numbers, so a high percentage uncertainty doesn't actually lead to a very big uncertainty in that value. But we'll get to that later on. The same process for the amplitude, but this time we don't have repeat readings for the amplitude, so we're going to use the resolution of the measuring device as a way of guessing what the uncertainty is. So I started the same way. I did 10 to the power of minus 1.22, and I've used uncertainty of 1 millimeter. So a meter ruler is an analog measuring device, so you'd have expected to see the uncertainty is 0.5 millimeter. But remember, to measure length, we take 2 readings from our ruler and find the distance between them. So that's why it's 1 millimeter there, because we've doubled it. So we've got A max and A min. We found log of A max, log of A min, found the difference between those divided by 2, and we've got our uncertainty in our first value of log of amplitude. Gone through exactly the same process for the log of the second amplitude, minus 1.96, and got an uncertainty of 0.40. And did for time period, I've added the 2 uncertainties together, calculated the percentage uncertainty using the value of the change in log A, giving us a percentage uncertainty in the change in log A of 6.3%. So now we can figure out our percentage uncertainty in our gradient. We can add our 2 percentage uncertainties together. That tells us the gradient has a percentage uncertainty of 99%. Then we can calculate what the actual uncertainty in the gradient is. So if we do 99 divided by 100 times by the value of our gradient, which was 0.0322, we end up with a value of 0.032 for the uncertainty in our gradient. So that means our gradient is anywhere between the values of 0.064 as its upper bound and 0.00039 as its lower bound. So we are expecting the value to be 0, but the value of 0 is not in the range of possible values for our gradient, so our experiment does not agree with the theory. It's very close to agreeing with the theory, but at the moment it doesn't justify the equation that we have for simple harmonic motion, which is not unusual when you actually do experiments properly. So that concludes this video looking at uncertainty in log of different properties and how we would find powers in equations using logs. I hope you found this video useful. If you have any questions about what I've done in this video, please feel free to comment and ask me, and I'll try and answer them as quickly as I can. But thank you very much for taking the time to watch.